don't know him. I believe that if you ask a research mathematician who has more than 35 years old and does geometry, what would you say are the two most important results in geometry in the last decade? Say in the last 10 years, what do you think the most important contributions to geometry are? And I think that everybody agrees that the first answer everybody would say, well, Perelman's contribution to the Poincare conjecture and to the geometry of three-dimensional manifolds. And then I personally believe that the great majority of the mathematicians that you would ask would reply. The second question is the contributions of Fernando and Andre Neves to geometry. What they did concerning the Wilmore conjecture not only solved a major problem, but it also introduced techniques that have been used subsequently to prove many interesting theorems, in particular by Fernando's very brilliant students. He's managed to produce a fantastic number of brilliant students, many of whom you will hear give lectures here about their work. So that's enough for presentation. Fernando.
Okay, thank you. I have mine here. Okay, thank you for the introduction, Harold. Before I start, I'd like to register two things. First, that it's an honor for me to have Professor Manfredo in the audience. It's a great honor for me to have you here, Professor. And also, I'd like to register that this school is happening just after a few months after the 75th birthday of Harold Rosenberg. So sorry, Harold, for telling how old you are. But I think it's really a great opportunity for us to reflect on Harold's career and his impact on mathematics in general, but also Brazilian mathematics. So Harold has been a major force in geometry and has influenced several generations of mathematicians. And I myself admire you very, very much. So thank you, Harold, for your immense contribution, and happy birthday. Okay, so I'd like to talk about minimal hypersurfaces today. So I'd like to talk about my recent works with Andre Neves on the general theory of minimal hypersurfaces. So basically, we are interested in the problem of given a Riemannian manifold, how many minimal hypersurfaces does the manifold have, and can you say anything interesting about these surfaces? So it turns out that there is a theory to produce these surfaces. It's called the Almgren-Pitts Mimax theory, which we have used recently to prove some applications, including the proof of the Wilmer conjecture. But it turns out that the theory is incomplete. For instance, it doesn't give much information about the Morse index, any information at all, actually, on the Morse index of these minimal surfaces. And that's what we are currently working on. So let me fix some notation. Throughout this talk, I'm going to denote by m, n plus 1, the metric G, a compact Riemannian manifold. And I'm interested in the n-dimensional area functional. And the question is there a Morse theory for this function? Can you say anything interesting about its critical points, Morse indices, and so on? And I'm going to restrict dimensions, ambient dimension between 3 and 7, just because in those dimensions, the hypersurfaces that you construct are actually smooth everywhere. So it's possible to consider also high dimensions, but then the minimal hypersurfaces will be singular in small sets. So for simplicity, let's assume that the dimensions are between 3 and 7. So basically, until very recently, the best result was the following. Was a theorem that can be attributed to Almgren and to Pitts, which basically says that there's always a minimal hypersurface. So for any compact Riemannian manifold under those conditions, there is at least one smooth, closed, embedded, minimal hypersurface. Let's say sigma. That's the theorem. There's always at least one. And it turns out that this sigma is actually produced by Mimex, by the Mimex method over one parameter sweep outs. And I will explain what this means in a second. So there's always at least one, so that's very nice. But the conjecture that we're interested in actually says that there are many, many more. So we call it the infinitely many conjecture. This conjecture is actually due to Yao in the particular case that the ambient dimension is equal to 3, but we can update the conjecture to higher dimensions as well. So it says that actually there should be infinitely many. There are infinitely many minimal hypersurfaces. When I say minimal hypersurface, I mean a smooth, closed, embedded one. So I think in the earlier version of the conjecture, Yao proposed immersed, but really the technique automatically gives you embeddedness. So we propose that the conjecture be updated to the embedded situation. And then what I proved with Andre a few years ago was that this conjecture is true if the Ricci curvature of the metric is positive. So that's what we proved. And we also proved that in general we can improve the result of Amgram-Pitts. In general, the number of minimal hypersurfaces is at least the ambient dimension is greater than or equal to n plus 1. Okay? But the general case is still open. And here's a case that we don't understand. So if you think of a dumbbell, say in S3, with a metric like this, you can visualize these 3 minimal surfaces. These are all, there's a stable one here, 2 unstable ones, minimal surfaces. But we can't find the 4th one. Right? So summarizes what we don't understand in this theory. So let me talk now about the method used to construct this first hypersurface. So what you do, is, as I said, to prove this theorem, we have to use Mimex over k parameter sweep outs. But let me first describe the one parameter case. So what you do is you choose your favorite Morse function. So here's a manifold M. So you choose a Morse function F. Say that goes, say this is 0, this is 1. F is a Morse function. And then you look at the level sets of F. Maybe there's a singular point here. That's okay. That's okay because we're going to use geometric measure theory. So you denote by phi naught of t, say the boundary of the set of points where f is less than t. And you see this as a hypersurface inside M. So this is a one-parameter family of hypersurfaces. So you can visualize this map phi naught as a map from the interval 0, 1 to the space of hypersurfaces with no boundary. In geometric measure theory, this has a name, so the notation that we use is this. We forget about orientation, so actually the coefficients are Z2 here. And for those who are familiar with geometric measure theory, these are basically flat chains modulo 2 with boundary equal to 0. But if you're not, that's okay. You just think of this as the space of closed hypersurfaces in your manifold. Okay, maybe you have a sum of them with coefficients in Z2. But this map is continuous in the relevant topology. Just to have an idea, you say that two things, say, for instance, two cycles, they're going to be very close, say T1, T2, in the flat topology if the region in between is very, very small. So that's one way of seeing this topology. So very weak topology in that space. But once you have one non-trivial family, you can define its homotopy class. Relative to 0, 1. So see that when t equals 0, this is the trivial surface, and when t equals 1, this is again the trivial surface. So it's actually a closed loop in the space of cycles. So you take the homotopy class of phi naught, and then you do the mi-max. So for each sweep out, you look at the maximum area. So you take the supremum of the mass. The mass is just the area. And then you minimize this over all families in your class, and you get the mi-max number L of pi. And then you prove that this number is always positive, and it's actually the area of a minimal surface. So let me write down what the statement is. The subject is a bit technical, so I have to oversimplify in some parts here. But basically, once you have set your mi-max procedure, what you're going to do is you're going to choose a mi-max sequence. So what is a mi-max sequence? Mi-max sequence is just a sequence of maps in the class such that the sup of the masses of the family is converging to the optimal number. Then once you choose the mi-max sequence, what the theory tells you is that after passing to a subsequence, okay, you can find points in the domain such that the surfaces phi I of ti, they are going to converge. And here the convergence is actually in the sense of measures. So for those who know, this is in varifold sense. So you have to forget about the cycle thing here and really consider the measure associated to the surface. But anyway, these are going to converge to some v, which technically is a stationary integral varifold with mass equal to the mi-max number. But the important thing for us is that the support of this varifold is going to be smooth. So the important thing for us is that V is actually a linear combination like this. Sigma i's form a disjoint collection of minimal hypersurfaces, and the ni's are positive integers. And then you get your minimal surface. Okay, so you do the mi-max. The theory will tell you that some surfaces in the families are going to converge in some measure sense to a nice minimal surface, but this minimal surface could be disconnected, and each connected component can come with multiplicity. So something like this could happen, that maybe the surfaces are developing a neck and are converging to twice a nice minimal surface. But the convergences are very, very weak. So that's what the theory does. I explained the method for one parameter sweep outs, but actually one can replace the interval 0, 1 by anything, let's say of finite dimension, say by x, k-dimensional simple initial complex. And then you're talking about k parameter sweep outs if the domain is k-dimensional. Actually, it turns out it follows from the very first paper of Almgren that if you look at this space of hypersurfaces, it's very interesting. Almgren computed the homotop groups of this space, and then it follows from his calculation that this space is basically up to a weak homotopy is equal to RP infinity, the infinite dimensional projective space. And that's interesting because this RP infinity contains RPKs for every k. So you can repeat the MIMAX process for every such, not only for RP1, the first family, but you can do it for RP2, RP3, RP4, and so on. And you can get a sequence of numbers. You can get a sequence omega 1 of volumes or areas associated to this RPKs, and that's how we prove this theorem. That's how we prove that the conjecture is true if Ricci curvature is positive. Okay? So that's a brief summary. But the problem that we face now, so the problem that we face is how to characterize the index. So characterize the index and the multiplicity of the surface. These are the major questions in the field. The theory said nothing about them. Okay? So heuristically, one should expect that the index of the variety should be, say whatever it is, bounded from above by the number of parameters. Okay, and here's why. You just think of a simple example. You're looking at the height function here. This is the height function, and then the height function on the surface has a critical point here of index equal to 2. So if you try to obtain this critical point by a one-parameter family, right, you're going to fail because you're going to realize that because the index is 2, you have enough space to deform the family, go around. So the sup of the height function becomes strictly less, right? And then you make it better. So that this guy cannot be obtained by a one-parameter max. It has to be a two-parameter. So that's why one expects this thing here. And actually, there is one situation in which one can completely characterize everything. This is a recent theorem with Ketover and Nevis. So there's a particular situation, but in which you know everything. So basically, you assume that you are in positive Ricci curvature and that you're talking about one-parameter sweep-outs. Then the theorem says that the MIMAX variety is going to be one single component with multiplicity 1, where this single component is two-sided and has most index equal to 1. Okay? So maybe I can try to sketch why this is true. So brief sketch. So the two-sided case we had understood before. So the idea is that if you have a two-sided unstable surface, right, you're assuming that the Ricci curvature is positive. So you can deform the surface in the direction of the first eigenfunction of the Jacobi operator. And then the picture is going to look like this. The areas go down. And then you're going to have some sigma epsilon, and some sigma minus epsilon, such that the area falls by some constant times epsilon squared. Okay? If you write these surfaces as graphs over the central surface, then what you're doing is you're just deforming your surface sigma, which is the graph of the zero function, in the direction of the first eigenfunction. And then you get this picture here. But then the mean curvature of this boundary is going to be positive, and it's going to point in this direction, so you can do min-max with boundary here. You can consider all sweep outs that start with this boundary and end at the zero surface, and you can try to do min-max here. So the conclusion is that there's going to be two possible pictures. So either every sweep out increases the area, something like this. But if this is so, then you can do min-max, find another minimal surface. Then you have two disjoint minimal surfaces in positive Ricci curvature. That's a contradiction by Frankel property. You cannot have this picture. So therefore, this means that there must be one sweep out with controlled areas, right, on both sides of the surface, such that the areas are bounded at most by the area of the initial guy. But then you say, if the index of the initial guy is greater than or equal to 2, then it means that you have a second eigenfunction to play with. And then, like in the previous example, you can just go around and make the area go down. So if the index is bigger than 2, you can connect sigma minus epsilon to sigma epsilon with area less than the area of sigma. And that's a contradiction, because you made a sweep out which has less area than the area of sigma. So this was a two-sided case. So sigma cannot have index greater than or equal to 2. So the remaining case, which we only have been able to solve recently, was the one-sided case. So the one-sided case is a bit different. So the surface looks like RP2 in RP3, right? So we have two identified antipodal points here. And then the local picture is precisely the same, something like that. And then you have your sigma epsilon. So the area of sigma epsilon is basically twice the area of sigma minus a constant times epsilon squared, right? Because it's a double covering. But you can play the same game here and conclude that there's going to be a sweep out with controlled areas, right? Just like before. But now what I claim is that one can, so the claim is that one can deform sigma epsilon to 0 with areas less than twice the area of sigma. And that actually follows from what we call the catenoid estimate, which maybe has been observed before. But what the catenoid estimate says is that if you have two disks of radius r and distance h from each other, and h is very small, then the unstable catenoid, you can compute its area. This is not 3. And the area is going to be bigger than twice the area of the disk, but the excess is actually very small. It's actually smaller than h squared. So this is much smaller than h squared. In this case, if you consider a tube connecting these 2 points, you're going to have a picture like this. And the moral is that Ricci curvature tells you that the area is going to fall by epsilon squared. But on the other hand, if I open up a tube here, and the tube has to have the shape of the unstable catenoid, I'm going to increase area at most something which is much smaller than epsilon squared, so the net is negative. And then you can prove this claim here. So that's the idea. So we cannot have, let me mention that Shinzhou had previously proven that one-sided must have even multiplicity. So with this result and this reasoning, one can rule out the one-sided case. So this is one situation in which one knows everything. But how about in general? So how about in general? So now we can take even X to be a k-dimensional parameter space. And in the general case, again, this is very difficult because usually when you look at Morse theory, even in infinite dimensions, people are using some kind of Hilbert space structure behind. And here there's no Hilbert space structure. So there's no, I mean, the gradient flow will not work here, not as nicely as in other situations. There's no Palais-Mail condition to check. So it's really a hard situation in which the notions of convergence are very, very weak, right? So one has to come up with deformations theorem from scratch, actually. But here's what we were able to prove. So we proved that the heuristic is true when for the support of the minimal surface. So the index of the support of V is bounded by the number of parameters. So this is true. So the index of the support means the sum of the indices of the components. So I have to say that when we were trying to prove the Wilmer conjecture, this was our motivation. So we knew that a result like this would have to be true, but it was not available at the time. So we had to, fortunately, we had an indirect way of arguing. But now we have this theorem, and one can proceed more directly and simplify a little bit the proof of the Wilmer conjecture. So, as I said, the index of the support is the sum of the indices of the components. In this situation, one can have multiplicity, but I'm just not counting the multiplicity in the index here. So you can ask, what about the multiplicities, right? So we have a conjecture for that. It's called the multiplicity 1 conjecture, which is kind of analog to a multiplicity 1 conjecture that exists in mean curvature flow. So what we conjecture is that that a two-sided unstable component of a min-max minimal hypersurfaces must have multiplicity 1. Okay, so if the component is unstable and if it comes from min-max theory, the multiplicity has to be equal to 1. One cannot have higher multiplicity. So sort of the idea of this conjecture is to say that generically the multiplicities are going to be 1, right? At least for those components which contribute to the index. So in some sense, this theorem will be optimal because the components that are relevant for the index will have multiplicity 1. What we were able to prove was that this multiplicity 1 conjecture is true for one parameter sweep-outs. So that's what we proved, that this conjecture is true for one parameter sweep-outs. And if one assumes that if there is no one-sided component, then one can say even more. One can say that the variety is going to have the following form: an unstable guy with multiplicity 1 plus a bunch of stable ones. So this guy has Morse. Let's put 1, and these are stable. Okay, so So as I said, one has to come up with several deformations. My mouth is a bit dry. Just one second. So as I said, one has to come up with several deformation theorems to prove these results. But maybe let me end with two things. So one is a conjecture that I make with Andre. So we conjecture that for a generic metric, there should be a minimal surface of index equal to k, and area growing like cases to this power here. So this is a conjecture that we make. And maybe the final thing I would like to mention today is a theorem in progress this is joint with Yokumovich. Nevisan says that if you remember there was this sequence of volumes omega k's, what we proved is that, let me write it down, it's better. And this is a Weyl law predicted by Gromov in 2003. Okay, I'll finish here. Thanks.